Good afternoon, all. Well, first of all, thanks for making it through to the last session of today. I'm Soteris, and together with Ali, we'll be presenting Meta's function as a service system called XFaaS. Function as a service is a cloud computing paradigm which allows developers to run individual functions, but more importantly, without the need of managing any of the underlying server infrastructure. Developers only need to create their application's logic along with some metadata and then deploy that to the function as a service platform. And the first time the function is invoked through different events, there is a number of operations that need to take place to prepare a worker to be able to execute this function. And this might take time. This is known as the cold start problem. It involves launching a VM, getting the container image, initializing the container, maybe starting a language runtime, and so on and so forth. But once you do that, any subsequent invocation of the function can be almost instantaneously executed on that worker. However, if a function is not invoked for a considerable amount of time, then the container and optionally the VM are being shut down, and then you need to start the process again on the next invocation. And there are several works out there, including from the industry, that detail different aspects of function as a service systems. And here we are talking about Meta system, which is part of a private cloud, not part of a public user-serving cloud. Functions at Meta rarely handle user-facing interactive requests that might demand sub-second response times, and these are, at least at the time being, handled by a separate system. And the ones that are handled by XFaaS can exhibit very diverse resource usage characteristics, which is not uncommon for a function as a service platform. And I only have two examples here, but there is more stats across all function types in the paper. The first example shouldn't be surprising. There is a notification system which developers can use to launch notification campaigns. There are typically millions of such invocations per second, but these execute relatively fast and consume a few CPU cycles. On the other hand, we have platforms like the Morphing framework, which might run for minutes and consume orders of magnitude more CPU cycles than ordinary functions. And this is a platform which programmatically generates ephemeral functions which execute different data transformations on data stores. And any function as a service should be responsible of being ready to execute any of those functions, any of those workloads. And with function as a service, the responsibility of provisioning resources to be able to meet this demand shifts from users to cloud providers. So any overheads, such as the ones I discussed at the beginning of the talk, now these overheads translate to hardware costs to cloud providers. And despite function as a service being a rather popular research topic in the last few years, we do lack a quantitative understanding of the problem, mainly due to the absence of reports on the actual hardware utilization of large-scale function as a service platforms. And there are several factors that might contribute to the increase in hardware cost. One is obviously the lengthy cold start time, but also the high variance of load and the downstream overloads that might result from the surges in load. For this talk, we're not going to be covering the first one. There are details in the paper, and we'll be focusing on the last two challenges. And it shouldn't be a surprise that the high variance in load can result in hardware costs, but also equal overload the system and downstream services at the same time. And what you see on the right-hand side is some statistics that have been published previously, and it shows the graph of the received function calls, where it has been reported that the ratio of the peak to the valley to the trough can be as much as 2x. And at Meta, we measured this, and we found that this ratio can be even higher. So it can be 4x sometimes. And XFaaS runs the risk of severe waste if we don't provision the resources to handle this. More importantly, this goes to show that even if we completely solve the cold start problem, with meta does through a collection of methods that are discussed in the paper, we still need to over-provision to cater for the peak demand here. So if hypothetically we need 20,000 machines to serve, let's say, the valley load in this figure, then we need to somehow be able to auto-scale to 80,000 machines to meet the peak demand as well. And I'm showing this to highlight that we need a solution that will allow to smoothen out this load so we won't always have to over-provision for the worst case and having machines that are being often underutilized. Another challenge would be the overloads in downstream services because of a common interplay between the function as a service and different dependencies on the downstream. For example, at Meta, many functions do offline computations on the social graph database, we call social DB here, which is also accessed by online services that serve billions of users. And in the past, there was an instance that led to an outage of the social database, and obviously lots of unhappy users. And to resolve this issue, it took several hours throughout the course of a day where on calls they tried to identify the causes and bring back the availability of the database. And one of the sub-challenges of that process was that it was unclear which functions should be shut down or rate limited to be able to regain that availability. And this, again, is a motivating example, which actually motivated in real some of the features that went into the downstream overload protection here, to show that we need a solution that can be adaptive, ideally be fully automated, should be able to respond quickly to events like this one, and also be fine-grained that will allow us to handpick those functions that are responsible for the downstream overloads. And all the above challenges are tackled at Meta through a collection of methods. And then next I will show the high-level overview of the system, focusing on the queue-triggered functions. And then Ali will take a closer look at some of the methods that the system employs. So to initiate a function call, a client will send a request to a submitter. The submitter enforces rate limiting and forwards the request to a queue load balancer, which will then select a distributed priority queue to persist the function call until it completes. The scheduler will periodically pull function calls from the durable queues and store them in its in-memory function buffers. And then it was going to forward that to a run queue based on some parameters such as execution deadlines, criticality, which shows how important a function is. And from there, it goes to a worker load balancer, which is responsible for choosing the right pool of workers based, again, on some optimization on increasing memory hit rate of the JIT compiled code. I also want to mention that all this happened cross-region, and we do leverage opportunities to cross-region and load the balance. For example, when we enqueue to the distributed queue, these can cross-region. Also, the schedulers, they might dequeue from the queue of a different region. And this whole process is coordinated by several central controllers, such as the configuration management system, which stores function metadata, or a global traffic conductor, which periodically calculates traffic matrices which are being consumed by the scheduler when it comes to make those decisions from where to dequeue functions. And with this, I'll pass it now to Ali to talk about the methods that XFaaS uses.
Hi, everyone. My name is Ali Sahraei. I'm excited to be here today and talk a little bit more details about what we have built on XFaaS at Meta. In the rest of the presentation, I'm going into more details about two sets of features in XFaaS, deferred compute as well as downstream protection. In each of those features, I'll go over some of the design and evaluation based on the production data. The first feature that I want to talk about on deferred compute is reserved quota. Each of the functions on the platform has a quota associated with it, which is assigned by the customer. This quota is specified in terms of the CPU cycles that the function can consume on the platform. And when we want to enforce this quota, we need to transform this quota to the RPS. And we basically measure the average cost of a function invocation, divide the quota, and we arrive at the RPS level. The enforcement is done in the schedulers. Inside the scheduler, we have buffers for each of the functions, and we have logic that continuously takes items from the buffers and pass them to the run queue. Within this logic, we have throttlers. The throttlers are always consulting the central rate limiter, and central rate limiter system is a component that's outside our critical path, and it can inform the schedulers what RPS rate limit to use for throttling. And just for illustrating how this can help with deferred compute, we have a chart here that shows the quota consumption of a function, and during a surge in traffic, it hits the quota limit, which is shown in red, and during the period that it's hitting the limit, it's creating a backlog in the durable queue. And during that time, all these items are going to experience some delay. We also have a different flavor of quota, opportunistic quota. In opportunistic quota, the enforcement and throttling is very similar to the reserve quota. The main difference here is that the throttling rate that we're going to use for these functions are going to be adjusted based on the worker utilization. So the higher utilization we have in our workers, we're going to have a lower throttling rate, and we're going to throttle these functions a lot heavier. And the lower utilization we have during off-peak hours, we're going to let these functions to execute more often. So overall, we're able to use this feature to defer execution of this function to off-peak hours. And because of that, we offer the SLA of 24 hours to the customers. Now, there's a few other features in this area. We have per function criticality level, and we have explicit future execution start time. In the interest of time, I'm not going to cover this in the talk, but if you're interested, please refer to our paper. Now, let's look at some of the results in production. The chart that we have on the right side shows the total CPU cycles consumed by functions. In orange, we're showing this metric for functions using reserved quota, and in blue, we have this for opportunistic functions. And this is a plot over 3 days. So as you can see, the reserved functions consume majority of the CPU resources in the system. But you can also observe that there is a daily peak here. There are a few hours that majority of our resources are used by these functions. The most important takeaway from this graph is that the pattern of the quota consumption by opportunistic functions and reserved functions are complementary. And this feature basically behaves exactly as we expected, which is able to defer the opportunistic functions to off-peak. Now, let's look at all these features and see how they work in production. So on deferred compute, we have 4 features: reserved quota, opportunistic quota, per function criticality, and explicit future execution time. We also have cross-regional load balancing. As Soteris mentioned in the system diagram, we are able to actually route traffic to different regions based on the worker utilization. And that way, we're not going to end up with one region that's running hot and another region which is underutilized. So in combination, having all of these features, we're able to flatten the execution curve of our functions. On the chart on the right-hand side shows the number of functions that are received by the platform in blue. And this is a chart that's plotted over 1 week. You can see there's a large peak-to-trough ratio. This number is 4.3. This is the exact chart that you saw in the beginning of the talk. We're also showing the functions that are actually executed in the platform in orange. And the peak-to-trough ratio is reduced to 1.4x. So this is a significant reduction in the spikiness of function executions. And overall, having all these features in production, we're able to actually achieve 66% daily average CPU utilization. Now, switching gear, I want to talk a little bit about our downstream protection features. The main feature we have in this area is back pressure handling. This feature relies on the signal that comes from the downstream services in the form of back pressure exceptions. The central rate limiter continuously looks at these exceptions, and once they're hit the pre-configured thresholds, it engages an AIMD algorithm for throttling. This is obviously inspired by TCP/IP, and we use AIMD here to define what rate we want to use for throttling the functions that are using that specific downstream service. Now, just to illustrate this a little bit more, on the chart on the right-hand side, you can see that when we have a situation that the back pressure exception threshold is hit, the AIMD goes into the multiplicative decrease phase. And in this phase, we reduce the RPS rate limit that we enforce for throttling significantly. And we continue to do that until the back pressure situation is resolved, where the algorithm goes to the additive increase mode, and we're able to gradually increase the execution rate of these functions. Now, let's take a look at how this feature worked in production. So we have a real incident to illustrate how back pressure handling worked. In this incident, we had an overload of a write-through cache that we have in front of social DB called tau. And in the first chart, you can see the read availability SLO of this service. At the start of the incident, the availability of the service went down to 90%. And in the two charts below, I'm showing two specific functions on the platform, and I'm showing the execution rate of their functions. Now you can see that instantaneously the execution rate of both of these functions went down almost to 0. And as the downstream services started to recover, you can see that these functions gradually started to increase their execution rate and go back to normal. Now, overall, in this incident, we were able to recover within 2 hours, and we didn't have to do any manual intervention to help with the recovery. And we were also very selective. We only throttled jobs that were actually accessing the downstream service. So to summarize, XFaaS is a hyperscale serverless function offering at Meta. It processes trillions of functions per day on more than 100,000 servers and more than 10 regions. We utilize the concept of universal worker to eliminate cold start. But we also, in this talk, we emphasized, even if we solve the problem of cold start, there's a large peak to trough ratio of the traffic. So without being able to soften the, reduce the peak to trough ratio, we would have to have underutilized machines and auto scale up to 4x to be able to handle that traffic. With the methods that we showed in this presentation, we're able to actually smoothen out the execution curve and get the daily average utilization at 66%. We also covered some of the features that we have for the downstream protection. Thank you so much for your attention, and with that, I'm going to open up for Q&A.
We have time for a few questions.
Hi, Anna Klimovic from ETH Zurich. Really great work. It's cool to see how serverless is being used in private clouds as well. I have a question about fault tolerance. Since from the client to the actual worker node pool where things get executed, the request seems to travel through a lot of separate components. You mentioned the queue load balancer and other components. I'm wondering if these components fail, does the system keep track of which requests are in flight, or is there chances that function invocations may get lost if components are failing?
Yeah, that's a great question. So a lot of the services in that data path are stateless and they're replicated. So that's one of the ways that we tolerate failures. And the queue is the service that has a storage. Mm-hmm. So if any other service so basically the queue is the only stateful service. Everything else is stateless. So stateless services go down, they can come back up and get the items from the queue. And on the queue itself, we use replication, and that's how we do the fault tolerance.
Okay, thank you.
Hi, Matthias Hille, Barkhausen Institute. Thanks for the insight in the real world. at what level do you schedule to defer computation? Is it invocations only, or is it also kernel level threads, or do you have user level threading?
I didn't get your first part of your question. Can you repeat that, please?
So how do you, at what granularity do you schedule? Is it only function invocations, or do you also schedule multiple functions on a single core?
Our scheduling is mainly function invocation specifically. So the buffers that we have in a scheduler, each item in the buffer is corresponds to one invocation. If that answers your question.
Yeah, yes, thanks.
We'll take a question on the far right. My far right.
Okay. Hi, João Barreto from Lisbon University. How does this affect the latency of the deferred requests, and if that has any implications on SLAs that you might have?
Yeah, that's a great question. So it depends on the type of quota that the functions have. So for reserved quota, we have a tighter SLA in the order of seconds, assuming that they don't hit their quota. For the opportunistic functions, however, we may throttle them heavier even if they don't hit their explicit quota. And for those ones, we have an SLO of 24 hours.
In the middle.
Hi, Zhang from Peking University. I see that you use AIMD to handle the back pressure. So how do you tune the parameters of AIMD? I think that you need to tune the parameters according to your social DB, like tau. But what if you use another backend service that has different capacity? And I'm also curious about, do you have any optimizations about scheduling serverless workflows? I see you schedule on the function granularity.
Maybe focus on just one question for the sake of time.
Sorry.
So on the topic of AIMD tuning, we do it empirically. So we have run this system for a few years, and based on the data that we get, at what level they become dangerous for the downstream, we decide on the thresholds. Same with the parameters. We empirically tune them in a way that they're relatively fast to respond to the functions, but they don't also keep throttling them forever. And so on one hand, you want to have the downstream service happy. On the other hand, you want to have the customers happy because you want them to recover relatively quickly after the issues with the downstream. So a lot of this is actually done empirically and based on the experience over the past few years to find the right parameters.
Thank you.
Shubham Mishra, UC Berkeley. My question is related to the last question. So you talked about AIMD. Is there a specific reason to use AIMD, or have you tried a bunch of different other congestion control algorithms, like delay-bounded congestion maybe?
So the main reason we use AIMD is basically the fact that it can react very quickly at the beginning of the incident, and the recovery is gradual, because we don't want to recover quickly. That can cause a whole bunch of other problems with failures and retries. So that's the main reason we chose it, but we really haven't compared it to other algorithms to see how it would differ.
Thank you.
And one last question.
Cristina Basescu, EPFL and Digital Assets, Switzerland. Very nice talk. So I was wondering, so to smoothen these spikes that you see, you might, say, schedule functions across regions, right? Load balance them. So I was wondering if you could comment on the latency that this adds to the function execution. Like if these regions are, there is some latency between these regions. Thank you.
So I don't think we have the exact numbers reported in the paper. What we have in terms of the latency is going cross-region costs us 100 times or more than that compared to staying in the region. So the way that we tackle the cross-region communication is we try to keep everything in region as much as possible. And then if there is any leftover that if we want to get more efficiency, then we go for cross-region, because then we would incur, that level of increased latency.
Thank you.
Thank you very much, and let's thank the two speakers once again.